So today we're going to talk through a change that we're making to the ActiveStore PanFS project, the product. There's changes going on in the workload in the HPC data centers. We're seeing a lot of public cloud kinds of technology move into the HPC data center, and some enterprise requirements as well. And a lot of sites are seeing a lot of change in the workloads that they experience coming from their compute cluster to the storage. And so we are, and the last point here is an interesting one. I find interesting that there are application types in the modern HPC data center where the engineers are more concerned with their algorithms than they are with the impact it has on storage. They want to create lots and lots of little files in a directory because that's convenient for them. And that's okay because they're focused on their algorithm, the outcome from that algorithm, not on whether they're nice to our storage. So that's an opportunity for us to solve that problem, and a win-win for both of us. They get to continue down their path, and we get to provide a product that they're interested in purchasing. So we have a project called a Ludicrous Mode Development Effort for extreme acceleration. And what we're trying to do is decide exactly what architecture is going to work best to meet those requirements. We need to retain our high bandwidth mixed load workload performance that we have today and low TCO, but we want to add ultra low latency and metadata intensive workloads to the workloads that we support. We want to retain our commitment to COTS hardware, right? Because we're on COTS now. That's taken us a while to get to full COTS, and we put value on that. And cost-effective high-performance solutions rather than performance at any price. Okay, so here is what we're going to need. We need bandwidth and latency. This is sort of the requirements that we see, the net sort of overall requirements for the project. Ultra-low latency, the right performance profile for each workload or data set. So out of all the different jobs that are running in the data center, this one needs low latency and that one doesn't, and we want to let the customer choose which one they get, that this file needs latency and that one doesn't. Fast metadata, we want to remain transparently integrated. So /PanFS is where the mount point for all of the applications to access our storage, and we want the low latency storage to be integrated into there, not as a separate piece, but just part of the characteristics of the system. I'll describe more about that in a minute. Leverage commodity NVMe over Fabric servers. They're a commodity out there now, and they're very low latency, so that seems like the right foundation to base it on, and cost effective as well. Okay, so in terms of Brasstacks, what we're talking about here is our existing product, the OSDs, stay as a tier 1 bandwidth optimized solution, and we're going to add a tier 0, which is the Fabric layer. That's the low latency layer. But we're calling them tiers because the data is going to move from the tier 0 up to the tier 1 up to tier 0 and back again transparently to the application. But the application will see the performance difference that results from the data being moved to one place or the other. As it says, bandwidth and latency. Our directors, that's these guys here. This is the storage devices in our current product, and then the green here is the new stuff. So we'll take care of all of that management, managing the hardware, managing the data movement back and forth, coherency, so that you're not seeing different behavior. It's all POSIX compliant behavior you're going to see. Just some things are faster than others. Some things have higher bandwidth, some things have lower latency. Okay, so this is it's easy, a good way to present it as there are typical worry points that customers have, and so I want to just address a couple of them here. Conventional wisdom is pessimistic. Conventional wisdom says, oh, you got to have all flash. We've taken apart each one of these requirements and have looked at the underlying challenges, and we believe we have answers to all of those different questions. So that's why they're listed this way. They're engineering issues. They're not actually laws of physics, as I say there. So all-flash storage is always the answer. First and foremost, and again, this is about sort of getting people to think about the problem rather than just assume that it's a challenge, right? All flash is usually too expensive. At the capacity points, $1,000 a terabyte, that's just a lot of money, right? We think we can deliver the same performance at a much lower price. It's probably not an LRU cache. This is a technique that we could use, but the problem with an LRU cache is that the first access wants to be fast. In an LRU, the first access is going to be slow, it pulls it up, and then later accesses are fast. So we don't think that that's really what the customer wants. We also want a small file, for example, to have good performance through its entire life cycle. And that's not really an LRU cache either. So we think that means it's a tier, right? Another challenge, people believe, parallel file systems like PanFS are high latency, just inherently so. The product we've just GA'd this last week, ActiveStore Ultra, we believe is actually going to have very good latency for a parallel file system. We store large files on hard drives. They're actually very good at delivering bandwidth if you don't give them anything small to work on. And so we put all the small files on SATA SSDs. They're actually SATA SSDs are very good at IOP workloads that come from small files. Metadata is very latency sensitive, so we put it in a database on an NVMe drive. So we're reading the raw horsepower of the NVMe drive and the caching behavior of a database. So if you throw a mixed workload at that kind of architecture, each of those storage devices is doing what it's good at. And so it's very efficient that way. But having said that, this is good latency, but we need ultra low, right? So there's still work to be done beyond that. Another challenge, ultra low latency is really hard to do. Well, not really if you're explicitly designing for it, right? The NVMe over Fabric boxes that are out there in the market today are very low latency because they have been designed specifically for that purpose, right? So the question is, how do we design for that purpose and to integrate it into PanFS? So this is one example of how we could do that. We're not sure this is the one we want to use yet, but a shared file system architecture. CXFS is an example. CXFS is an example of that. GPFS used to be an example of that. They've modified it over the years. An NVMe over Fabric box is basically like a fiber channel disk array from a long time ago. It's a shared storage. You can have a lot of people access it simultaneously. And so that's a design model that we think would work. The challenge is that shared file system architecture has challenges with multi-host sharing. That's its big issue. The performance of, if there was only one node using it, you'd have local file system performance and it'd be blazing fast. Once you go to multi-host sharing, that's a challenge we'd have to solve. So this is here's a good part, and here's a challenge, and you'll see the rest of the topics have that too. Another thing, POSIX is slow and doesn't scale. POSIX proper is just directories and inodes, directories and files. And so the vast majority of POSIX operations are going to be one inode, maybe two, the directory and the file itself. And so out of hundreds of millions to billions of inodes in the file system, that's what people normally call embarrassingly parallel, right? Because there's only one or two for this operation, so you don't need a lot of locking there. Where the problem really comes in is in the file system metadata that holds that. This is the payload, and it's the allocation groups, the free space maps, and the super blocks, and a whole bunch of other stuff down here that holds this. That's where the bottlenecks come in. Now, the reason that's important is you have to solve the right problem. If you're focused on this, that's not going to be your problem, and that's so focusing on improving POSIX performance per se is not the issue. It's down here. Fortunately, these data structures aren't visible to the end customer. They only see these, right? So we have freedom to go reorganize these in order to fix this, right? The multi-host sharing, we have the ability to change the data structures that carry POSIX in order to fix that problem. Now, okay, so how do we separate POSIX from file system metadata? So ACID is a term that comes from the database world. So your atomicity, consistency, independence, and durability. If, for example, you want to take you create a file and you want to make sure that file stays created for forever, for the rest of its lifetime, you would need to update the POSIX data structures and then sync out the file system metadata. And So if you're willing to relax durability and wait before you sync it out, then you can actually get higher performance. And I mean, this is basically what we do in Tier 0 scratch in an HPC world, is you say, okay, there is some risk that the Tier 0 might not survive an outage. And so we're test driving that to see if we can reduce the impact of an outage, but still get these benefits, right? And almost the last slide here. So everybody says policy agents are required for tiering. Well, yeah, and they're hard. Well, yeah, but you don't need to. So they're hard, so don't do that. The way we're proposing to do this, PanFS, you can run your application against the PanFS file system and it'll just work. You won't get the benefits of the new tier of storage unless you give us a pre-action and a post-action. Just set an extended attribute saying, yeah, those particular files, I want low latency. We'll move them up transparently to you. We'll move them up into the latency tier, and then you get the performance you want. And then afterward, we'll move whatever result you want back down. And then we'll tear down the latency tier infrastructure that we used for performance, right? So everything will work, but you tell the application, but if you do this, if you identify the files you need at low latency, then your job will run much faster. So we think that that'll actually motivate them to do the extra step for us and avoid the complex policy engine. So, conclusions. We see the need for ultra-low latency storage. AI and machine learning and GPUs are one of the prime examples where you need a little bit better latency, maybe a lot better latency, especially if you're doing inferencing. There's all other things like IONEDs and InfiniBand clusters are how you do a large IO and then you parcel it out to the nodes that actually need the data. But that's a way of masking the high latency of the traditional parallel file systems. And we're working on it. Ludicrous Mode is a research project, and we're in prototyping and proof of concept mode, trying to find the best architecture, and then we'll go off and implement it, and we'll let you know as we go along how things are with the project. So, questions? Cool. Well, thank you for your time.